Welcome to today's SCA webinar with Artificial Neural Systems Provide Wolfcamp Completion Design Insight with Bob Shelley. Before we start today's webinar, we'd like to ask the audience a few questions about the demographics of the audience. So I'm going to launch the polling questions. And the first question is, what's your primary discipline? So we're starting to get responses. It looks like we have quite a few petroleum engineers in the audience. Responses are still coming in, but petroleum engineers followed by geoscience. Looks like it represents most of the audience. We have a few people with petrophysics background as well. We're still receiving responses. So most of you have voted now, so I'll go ahead and close and share the results. We have 50% petroleum engineers, 25% geoscience, 17% petrophysics, and 8% other. So the next question is, how many years of full-time experience do you have in the upstream oil and gas industry? So we're getting quite a few responses, some in every category. The majority of you have voted now. So I'll close the poll and share the results. We have 46% with over 30 years experience, and then it's a tie in several of the other categories at 15% for 21 plus, 11 plus, and 1 plus, and then we have 8% with less than 1 year. So thanks for participating in the polling. I'm going to share some slides here so we can start the introductions. This is Artificial Neural Systems Provide Wolfcamp Completion Design Insights. And I'd like to remind the audience that you are muted, but you can ask questions during the presentation using the GoToWebinar question feature, and we'll cover the Q&A at the end of the presentation. You will be anonymous. So I want to introduce Mr. Bob Shelley. Bob has more than 40 years of experience in well completions, hydraulic fracturing design, and reservoir evaluation. He's worked on projects around the world in a number of different countries. He served as an SP Distinguished Lecturer twice. His first presentation was on completion design. His second presentation was on completion design using AI and machine learning, case histories. And then his first presentation was optimization of multi-fractured horizontal completions, a new industry challenge. He's also served on the Well Completion Committee for the SP Annual Conference, chairing that committee twice. He's published over 40 technical papers and holds more than 10 patents. Bob has a BS in Civil Engineering from Colorado State University and a business training from OU and East Tennessee State University. So Bob teaches a class for SCA entitled Artificial Neural Systems Provide Wolfcamp Completion Design Insight. That class is offered in October 23rd and 24th in Houston, Texas. We have several upcoming webinars scheduled for SCA. Next week, we have Bob Barbet. He's doing a short look at how to avoid 60% EUR losses with protective refracts. Dennis Drea is speaking on what are you missing about your well and reservoir fiber optic sensing, could give you the answer. And Beryl Denderuk and Sylvia Levesque will be speaking on geothermal later this summer. We have some live online classes that are scheduled. In July, we have Energy Transition for Petroleum Professionals with Dr. Nathan Meehan. We have Dr. John Lee teaching 2 live online classes. One is Production Forecasting for Low Perm Reservoirs, and the second is PRMS and SEC Reserves and Resource Regulations. Both of those are scheduled live online in July. And of course, SCA training courses can be offered in your location as well as in our Houston Training Center. So contact us if you're looking to host an in-house course. In addition to training, SCA also provides consulting services on a number of technical topics, and we also provide projects and studies and direct hire services for both contract and full-time employees. So I am going to pass the presentation rights over to you, Bob, and let you start the presentation.
Okay, I'm going to minimize that and also bring up my PowerPoint in presentation mode. Pointer options, laser, got it.
You're all set.
All set. Okay, well, thanks everyone for attending this. You know, my course is actually artificial neural systems in petroleum engineering. It's more general, talk about a lot of other applications and uses other than what we're visiting about today. So with that, I'm gonna proceed and you know, give you a bit of information about background to this project. Actually wrote a paper on this and presented it at your tech a couple of years ago, 5572. What you're going to see today is a little bit of an updated version of that. But the purpose of this project was to improve the understanding of what drives Wolfcamp B completion production results. And we had this project was based on approximately 300 completions from a 9-county area in the Permian Basin. These wells or completions were selected based on data quality and completeness. And our objective was to develop a Wolfcamp B data-driven model, or something that gives us, you know, just based on the data that we have, the real world data, what drivers or what's most important to Wolfcamp B production. Here we're looking at a couple of scatter plots comparing several of the data, or 6 of the database parameters, to a normalized production on lateral length. And you know, just looking at this comparison, you can see you know, the challenge here, especially with the reservoir characteristics. There's not a whole lot of correlation there, but there is a positive trend with perm, pore pressure, effective porosity. If we look at the completion parameters, there's maybe a little more definable trend with total proppant per foot, total clean per foot, or proppant intensity and fluid intensity. And then looking at average proppant concentration, maybe a little bit of a negative trend, but it's, you know, it's kind of iffy there. You're really hard to hang your hat on anything. But you know, this, you know, I've done a number of projects where we analyze data. This is kind of typical of what you see with large databases, especially when you're bringing data from multiple sources and so forth. You know, there's some inconsistencies and you know, in the data, you know, maybe some bias in the data that makes these trends, especially the reservoir trends, I would expect them to be more apparent than what they are. So what we did with this project to try and suppress some of these data error issues and bias issues is we took the reservoir data, pore pressure, permeability, effective porosity, net to gross ratio, water saturation, brittleness, total organic content, and we used a technique called self-organized mapping, and we mapped these parameters into 7 different reservoir types. And you can see the scatter plots on the left there for perm versus production, pore pressure versus production, effective porosity versus production. for the raw data. And then the map data is on the right. We're comparing the same parameters, perm, pore pressure, and effective porosity. And you can see that the trends are much more apparent. And if we look at this in a little more detail, we can see that the the reservoir type that's above trend on permeability is below trend on pore pressure. Kind of offsets that impact. And the two reservoir types that are above trend on pore pressure are below trend on effective porosity. So they kind of offset each other. So this gives us some. Seeing these types of results gives us some confidence that there is some useful information here for us. Here we're looking at the reservoir types from a little different aspect. When we mapped the data, we didn't map anything other than the reservoir characteristics. And in the previous slide, we didn't map production. But we're looking at the average production. Again, a first year BOE per foot of lateral length for the 7 different reservoir types. And as you can see, the best reservoir types are over on the left, as far as production goes, and the worst on the right. If we look at this a little more detail, the best ones, number one, reservoir type number 1 on the left has the highest pore pressure and the lowest water saturation. Reservoir type 2 has the highest permeability and the highest net to gross ratio, and reservoir type 3 has the highest effective porosity. We look over on the other side, reservoir type 7 has the lowest pore pressure, permeability, net to gross ratio, and highest water saturation. Kind of helps. This, to me, this is very interesting because we mapped the reservoir characteristics, and the production again follows the the trend of the reservoir characteristics. And it also looks like there can be, when you're dealing with a good quality or reservoir, that can be attributed to a number of different factors, combinations of factors there. We did the same thing with the frac stage design. We mapped them again into 7 different frac stage types. And what we're looking at here and with the bar chart is the average 365-day BOE per frac stage in this case. And as you can see on the 2 ends have the highest, number 1, over on the left. It's got the widest stage spacing. It's got the most proppant per frac stage, and it's got the most clean volume per frac stage. We look over on the other end. Number 7 has high clean volume per frac stage and low average proppant concentration. So it kind of looks like this might be bimodal as far as frac stage effectiveness. If we look at in the middle there, where the poorest frac stage performance is, we can see number 3 has got the tightest stage spacing and the lowest fluid intensity. So, again, this, the arrangement of this follows a pattern, with what we would kind of expect to see, with bigger volumes in terms of, proppant and fluid and wider frac stage spacing gives us better production. However, on the far right there, there seems to be some issues, at least in some cases, with design or the way the proppant average proppant concentration. What we did next is we took our mapped frac stage type and mapped reservoir type and combined it into a matrix. In other words, we combined the different combinations of frac stage types with different combinations of reservoir. Where there's a value in this table, that is a, we had that combination of design and reservoir in the database. If there is no number there, that means we didn't have that combination in the database. If we look at this in more detail, we can see over there on the left, frac stage type 1 and reservoir type 2 is the highest 365-day BOE per frac stage value. And in the middle there, if we look at frac stage type 3 and reservoir type 6, it has the lowest. And if we look in the table underneath there, again, the combination on the left there has the highest proppant intensity and the widest stage spacing, and number 3 in the middle there, not only is it not as good it has the lowest fluid intensity and tightest stage spacing. Trying to analyze this data and looking at it in more detail is really difficult, and I had a client ask me to do that, and really the only way I know to extract information out of this is to take this data here and develop a artificial neural network on this data. For those of you that don't know what an artificial neural network model is, it's a form of artificial intelligence that can develop a relationship between known inputs and a desired outcome. They're basically crude electronic models based on the neural structure of the brain. They learn from experience. In other words, the data is presented to the model and it adapts through a training process. And the final point I want to make is the models can be trained on real world measurements like what we're talking about in the Wolfcamp B project today. Or you can develop a model based on a simulator and frac model runs, simulations and runs. If I was going to use depending on where the data came from, if it's simulator data, your strategy for model development would be totally different from the strategy that we're using today on real world data. The diagram there is a neural network model. As you can see, it's got 3 components: an input layer, a hidden layer, and an output layer. Neural networks can have a single hidden layer or multiple hidden layers. They can have any number of input values, and they can be any number of nodes in the hidden layers, and they can have more than one output node. These neural networks can be trained to multiple outcomes simultaneous, and that's just an idea. I'll give you a little bit of the terminology. The little connection arrows here are called weights, and it's these weights that are adjusted in the training process when the training data is presented to the model. Here's another very simple artificial neural network. Let's say we've got 3 input nodes, a single hidden layer with 2 neurons, and a single output node. And initially, before the model is adapted to the training data, these weights are all individually, just randomly assigned. And the first data records presented to the model It produces an output value. That output value is compared to the desired output value. And then the error is then back propagated back through the model. In other words, these weights are adjusted to allow the model to more closely match that data record. And the data is presented to the model over and over and over again until there's no further reduction in error. And at that point, the training process is stopped. The model, everything internal here is locked, set in place. And when you present new data to the model over on the left here, it gives you an output value based on its adaptation to the training data or the training process. So there are two modes. There's the adaptive mode where the model's learning on the data, and then there's the predictive mode where the model structure is set, everything's locked in place, the weights, and you present new data to the model and it predicts an outcome. One of the things that a lot of people are concerned about with neural networks is overtraining. And one of the ways we try and get around that, or one way to get around it, is to divide your data into two data sets. Training data that's actually the model is actually adapting to, and then test data that's held back for model evaluation purposes. And ideally, what you want to see happen in the training process is that on the initial data passes, you have high error, but then as the training process continues, more data passes through the model, the error on the training data and test data come down, and you reach a point where there's a divergence. If you continue training, the error on the training data continues to decrease, but the error on the test data will actually increase. And actually that's, based on my experience, that's basically where you want to be and where you want to stop the training process. Here's results of the neural network, or some sensitivities and some predicted versus actual production. A 365-day BOE per frac stage, model predicted on the x-axis, actual on the y-axis. And as you can see, the model that we developed here, we predicted the 4 outcomes simultaneous. Two different production data vendors. We have a BOE per frac stage over on the left from vendor one, data vendor one. We have a barrel oil per frac stage just to the right from the same data vendor one. This is data vendor two, BOE per frac stage, and vendor two, barrel oil per frac stage. The training and test data set, the data, as you can see, are shown. There's a similar trend on both. We have, this data set was actually fairly easy to train. The pre-processing of the data really helped out here. What we're looking at in the table underneath here is the sensitivities performed on the model that was developed for the Wolfcamp B. As you can see, if we increase pore pressure by 100 psi, we get a positive response across the board in BOE per frac stage, barrel oil per frac stage, as well as from both data vendors, although there is some differences. Well, by the way, we in this model development process probably spend a whole lot of time performing sensitivities on the model, because we want to try and understand how it behaves make sure that it doesn't behave in some way that doesn't make sense from an engineering or physics standpoint. Um, and we're looking at kind of a ranking here. The next most important parameter was porosity. If we increase it 25.25%, you can see a positive response across the board. Increasing cream volume by 1,200 barrels, positive response across the board. Stage spacing by 20 feet. In other words, you're treating a larger interval with one stage. Positive response, we kind of expect that. It's kind of like having more pay thickness per stage. Increasing proppant by 50,000 pounds, we get a positive response, but not quite as dramatic as the reservoir characteristics. Increased treatment rate by 5 barrel a minute. We get a positive response, but lesser magnitude. So I basically told you a little bit about how the model responds in this slide. What we're going to do next is we're going to take a look at, use this model to evaluate some Wolfcamp B completions. The first one we're going to look at here is in Midland County, 2016 completion. These are the characteristics: TVD 9710, lateral length 8704, 35 stages, plug and perf, 81 barrel a minute, treatment rate on average, 426,000 barrels of fluid, hybrid type fluid system, and so forth. Over 13 million pounds of proppant, mainly 40/70 with some 100 mesh. Proppant per stage average 373,000 pounds. Average proppant concentration less than 0.73. 365-day BOE, around 181,000, and 365-day oil, about 153,000 barrels. Pore pressure 4227, effective porosity 5.7. So what we're going to do now is we're going to bring this up. I've got the characteristics of this well. We're going to actually use the model to predict well performance for as completed, which is actual 35 stages, the first line here. And then we have 18 different completion scenarios. The first half are more slick water type completions, average proppant concentrations of 0.75 pounds per gallon. Then the next half of them, or next nine, nine are more of a linear gel, maybe hybrid type system, average proppant concentration 1.5 pound per gallon. 100 barrel per minute on all of these scenarios. As you can see, we have increasing proppant intensity and fluid intensity sequencing, 1,000, 2,000, and 3,000 pounds per foot of lateral length for the water frac treatments, 2,000, 3,000, and 4,000 pounds for the hybrid or linear gel type treatments. So let's go ahead and run this, make predictions for these 18 wells. Oh, by the way, these are 18 wells. It could be 50 wells, 100 wells, 1,000 wells. One of the things about neural networks is they're very fast, and hopefully, and that will be when we run the data through the model. Something fell asleep here. Let me change something. Let me fix something here. There we go. Finally got it up. The results are over here in the plot on the left. As you can see, we're looking at well production in red, 365-day cumulative BOE, and a 1-year well return on investment in blue. If you look at the table up here, the actual production was about 181,000. The model is predicting about 198,000 BOE in 1 year. Barrel oil, 153,000. The model is predicting about 147,000. This is actually, very good. I mean, these models are not 99% accurate. If we're getting in the 90% range, that's really, really good for these types of models. This is the way the well was actually completed over here on the far left. Completion designs 1 through 18. You can see the highest is right here on number 12. We come over here, 12. It's a 45 frac stages, 4,000 pounds of proppant per foot, 63.5 barrels per foot, 100 barrel a minute. One thing that's kind of interesting is generally the higher proppant concentration type treatments, and at least for this particular well, seem to be higher than the linear gel type treatments, which we're looking at right here, or the slick water, excuse me. One other thing that's interesting is that both of them with increasing stage spacing or decreasing number of stages for this lateral length have a decrease in model predicted BOE. So it kind of looks like the optimum number 12 is somewhere around 200 foot of stage spacing. More of a hybrid type frac design in this particular case. So let's move on to the next example I want to share with you. Let me go back to my my slide, Wolfcamp B. Let's go to a well in Upton County. Again, 2016 type vintage, 94, almost 9,500 foot TVD, 5,000 foot lateral length. This one was completed with 50 stages, 20 barrel a minute per frac stage, cross-link fluid, 14,000 pounds of proppant, all 100 mesh, 400,000 pounds of proppant per stage. Average proppant concentration over 3 pounds per gallon. So this is kind of unique. This was kind of I believe, an experimental well, just looking at the data. So let's go back to our model, and I'm going to clear this table here. We'll go back to our user interface. Let's just change this up here. We'll go Upton. $42.29, 5.5, 5,073 of lateral completion length, 94.84 of TVD. 365-day BOE is 146,570, and 365-day oil is 103,105. 50 stages, proppant intensity of 2,800, fairly high for that vintage of completion. 19.4 fluid intensity, 19.4 barrels per foot, and an average rate of 20. So let's run this well through our model. Okay. We look at our table here, we can see that the model 149,000 barrels is pretty close to the actual BOE, first year BOE. 111,000 barrels of oil versus 103 actual. Again, pretty close, reasonably close. I wouldn't say off by about 10%, but over here on the far left is what the model is predicted for this well as far as production. Right at just about 150,000 barrels BOE in the first year. Return on investment is with the blue line here. And actually, as you can see, if we look at this, it's kind of on par here as far as fracture spacings. And if we look at, they range anywhere from 113 feet to 203 feet. So this would be 113, 145, and 203. But the highest return on investment is over here on the far right. It's number 18. Again, it's more of the hybrid type system, 4,000 pounds of proppant per foot, 63.5 barrels per foot, 100 barrel minute. Roughly, again, about 200 foot of fracture spacing, 25 stages on that 5,000 foot lateral. Again, it allows us to look at, frac designs very quickly, maybe identify, ways to improve the frac design, or could be improved. Another thing, some of these frac designs, the way the well was completed actually performed better than some of the scenarios that we have here in our completion. I'm going to go back to our. I want to share one more completion with you, and Reagan County. Uh, 2015 vintage well, TBD 8256, lateral length 4,800, 28 stages, plug and perf, 74 barrel minute on average, all slick water, mainly 40/70, some 100 mesh, 6.3 million pounds of proppant. I don't know what happened to my pointer. Laser pointer. 365-day BOE of 66,000. First year oil, almost 55,000. So let's go back to our user interface here. Let me clear the results from our previous run that we ran through it. Just go through and put in the characteristics here, 3677, pore pressure, lower pore pressure, lower porosity, lateral length, 4854, TBD 8256, 8256, 66633, 54705. And it was treated with 28 stages, 28, get the right key there, Bob. 1,301 Proppant intensity, 28.4, and average rate, 74. Okay, let's run this one through. Let me fix this again. Oh, there we go. There we go. As you can see, again, without Excel kind of slowing down on me, it's pretty much instantaneous results. As you can see, in this particular case, the model is kind of under predicting a little bit. 50 is predicting about 54,000 BOE versus actual more like 67,000. 39,000 of oil versus almost 55,000. The actual design is over here. As you can see, there's this well was definitely understimulated compared to all these other designs. Proppant intensity was too low, fluid intensity was low. If we pick the highest here, both in terms of production and return on investment, it's number 6, which is 35 stages, 3,000 pounds of proppant intensity, 95 barrels per foot of fluid intensity, 100 barrel minute, 139 9-foot fracture spacing, so a little tighter fracture spacing. If we look at the compare it to design number 9, which is basically the same proppant and fluid intensity, but just lesser number of frac stages, there appears to be a benefit for a little tighter spacing on this particular well. Another thing of interest in this case here, the hybrid designs don't seem to be as effective as the slickwater designs. I thought that's kind of interesting. Basically, the data is what I believe it is telling us is that as you move across the field, that it's you wouldn't expect to have the optimum design to be the same. Needs to be taken into reservoir characteristics and so forth need to be taken into account as far to get the best well production. So with that, I'm going to go back to my PowerPoint here. Just want to close with this type of approach to completion evaluation offers a different perspective, is low cost and quick. A field or formation neural network model has multiple uses. Evaluate the performance of existing wells, like what I've demonstrated here with the 3 examples. It can be used as a new completion planning tool. Help us give us an upfront idea of what type of completion designs we need to be looking at. It can also be used to identify refrac or recompletion well candidates, wells that seem to be underperforming. They've also been used, models like this have also been used for prospect evaluation. In other words, how would these wells have performed if they were completed and fracked differently, maybe more effectively. The model development workflow used to develop here, this model can be applied to any formation in any basin and any well type, provided sufficient data is available. These models can predict not just a first year outcome, but a 6-month, 12-month, 2-year, 3-year, oil, water, gas, simultaneous, sand production as well. There can be many outcomes that these models can be trained to. And then, the last bullet there, data pre-processing using the self-organizing mapping was helpful to suppress systematic errors in this database. I can tell you this database was pretty much untrainable without this pre-processing step. And this step is it's intended to reduce errors, but also can reduce bias that's embedded in the database that can affect your final product of your model. So with that, I'd like to tell you about a class that's scheduled for October. What happened here? I lost it. Scheduled for October. Artificial Neural Systems and Petroleum Engineering will be, it's a 2-day class that I intended for persons that are experienced professionals that are not satisfied with or maybe want to take a different perspective or need ideas on a different perspective on how to improve production in a field of wells. It's a 2-day class, and the objective here is to give participants a fundamentals and develop a working knowledge of developing these types of neural network models. It's my intention that they'd be potentially capable of building a model like I demonstrated here today at the end of the 2-day class. And with that, I'm going to close it. I'll answer whatever questions there might be. And again, thank you.
Great, thank you, Bob. And we're starting to receive questions now. I want to remind our audience that you can submit your questions in the GoToWebinar question feature. Later today, you'll receive a link to the recording of today's webinar, an evaluation form, and a link to register for Bob's class on artificial neural systems and petroleum engineering that's scheduled for October 23rd and 24th in Houston, Texas. So one question from our audience is, can you please explain a little more on the binning process? How did you get the numerous data points into 7 bins? What was your workflow?
Let me, well, I don't know if I have that. Let me bring up a slide here. Am I still projecting?
Yes, you are.
Okay. The self-organizing mapping is a technique. It's been around for a while, but I think it's a very powerful technique, especially when we're dealing with field data and we have all these issues with it. What it does is it associates data records with similar characteristics. So we use those 7 reservoir characteristics, and the self-organizing mapping is actually a type of neural network model, but it uses a different type of training algorithm. It doesn't use back propagation training. It uses a winner-take-all training algorithm. In other words, it's called unsupervised training to assign like data records to a predetermined number of bins. And these bins can be arranged in either a linear array like what I'm shown here, or they can be a matrix. And the way this works is the winning bin's weights are adjusted to more closely match the data record. In other words, we've got 3 values here. We feed it into this neural network. There's going to be a winning bin here. In this case, it's bin 1, the red one. The weights to this bin are going to be adjusted to to allow that record to more closely, or bin one to more closely, the weights on bin one to more closely match that record. The adjacent bin two, gets half the adjustment. So these weights on bin two are adjusted. The weights on the other bins are not adjusted. The next data record's presented. There's a winning bin over here, and the winning bin's weights get a full adjustment. The adjacent bin's weights get half an adjustment, and so forth. Again, the data is presented over and over and over again until there's no further separation or differentiation between these bins. In that case, at that point, the training is stopped, and you can look at the characteristics of each bin. That's what we calculated in our tables in the presentation. So it's through a training process, and it's very powerful. What I think is really interesting and really is you can train on when we trained on the reservoir characteristics, and if you notice, the reservoir characteristics followed an arrangement, the same arrangement as the production when we calculate the average production for each reservoir type. To me, that's powerful. We're able to infer a production without really even knowing what it is. And the other thing is to me, the arrangement is very important because of this training process with the adjacent bins getting half the adjustment. We expect the adjacent bins to be most similar. Like in this particular case here, bin 2 is most similar to bin 1, bin 3 and bin 4 are more dissimilar. Bin 4 would be most similar to bin 3, and bin 1 and 2 the most dissimilar from bin 4. I think it's a very powerful tool, especially when we're trying to cut through some of these issues that we run into with this real world data.
Thank you. So the next question on slide 12. If you could go back to 12. So how did you decide what increments to increase the various parameters by?
Well, what we're doing here is we're basically performing sensitivities on the model. I picked 100 PSI because I wanted to give people something to relate to. But one of the ways I like to do these sensitivities is to adjust make the adjustment 10% of the range, and that can be done as well. In other words, there's pore pressure. Maybe it varies from 3,500 pounds to 5,000 pounds. So the range is 1,500 pounds. 10% of that would be 150 pounds. So you might increase it by 10% of the range. That's another way to do it, and depending on what values you pick, the model response might appear a little bit different from a relative standpoint. I just tried to pick values here that people can relate to: 100 psi, 1/4% of porosity, 1,200 barrels of fluid.
Thank you. So you mentioned that with trying to decide the point at which to select how much training data and how much test data to use, the test data would converge. Is there a trend to when that happens? Is it 50%, 75%, 25%? In your experience, what do you generally see?
I believe he's talking about this slide here.
Right.
Referring to this slide. Yes. Ideally, this is what you want to see. I mean, you want to see your training data and test data, they are to come down together. And in other words, you don't want to see, boom, you reach a point of minimum. You don't want to go up, go down this way and all over the place, and then boom, you reach. You want it when you're evaluating, when you're creating these types of models, having a model that trains easily, and this is what I would say trains easily, is preferred over one that, say, just randomly, just first crack out of the box reaches this point. I mean, there's some judgment here. There's some judgment here, but ideally, this is what you want to see. But this is not what you always see. You see a lot of crazy stuff in practice, especially with real world data. Simulator data, it's not so much of an issue.
So you mentioned in your conclusions that the self-organized mapping can suppress systematic errors. Could you elaborate on that a bit more, please?
Yes. Let me back up here. The information on the right is contained in the information on the left, in the data on the left. However, these trends on the right are not readily apparent in the data on the left. And when dealing with things like permeability, it's effective porosity. These things really aren't measured. It's not like measuring the width of your desk as 4 feet. I mean, they're indirectly estimated, and there are different. It's not. There's some systematic errors in that process, and by clustering in the different reservoir types, we are averaging out those systematic errors, basically, is what we're doing.
Thanks. Are you using any spatial relationships in your modeling? East side of the field, west side of the field?
Yes, we always look at that. And it's really, I don't have that slide here, but it's really very interesting to map the location of the 7 reservoir types on a map. It's very interesting. There's some geographic significance, but there's a lot of overlap too. So
sure. Great. Well, we're nearing the end of our webinar today, so I want to thank our audience for attending today's webinar. Again, later today, you'll receive a link to the recording of today's webinar that you can share with your colleagues, an evaluation form, and a link to register for Bob's class on artificial neural systems and petroleum engineering that's scheduled in SCA's office in Houston, October 23rd through 24th, 2023. Thanks, everybody. Goodbye.